Hello everyone, this is Anand Ranjan, Assistant Professor, School of Computer Application, Babu Banarsidas University, Lucknow. Welcome you all in the video lecture series of digital electronics. In this video, we will discuss the Ring and Johnson counter.
In shift register, if you provide the feedback loop from the last flip-flop output, and then you can able to have the two different type of counters. One is ring counter, and other is the junction counter. Okay, so let's start first discussing the ring counter today. Okay, this is ring counter. Okay. So as its name suggests, somehow there might be the counting process is gonna be repeat after some iterations, or you can say. So let me first write important note point regarding the ring counter. So number one, we have already discussed this statement most of the time when we have discussed the counter. So let me write this common statement as that n bit counter counts n states. Okay, n states, and in which you might have some used and unused states. For example, if you are assuming the used state, just we have seen in case of BCD, there are 9 used state and this 6 unused states. If you are constructing with the 4 flip-flop, so the used state, for example, you are considering as capital N is equal to small n, and unused state which is equal to 2 raised to the power n minus of n. So this is in the general case actually. Okay, now the second important point is if the input frequency am I audible and my board is visual to all of you? Yeah.
Yes, sir. Yes, sir.
If the input frequency is small f, the output frequency of each flip-flop is what? F divided by n. Yes, this thing we have already seen. That's why we have told the counters as the modulo n counters kind of thing. And at any instant only one flip-flop is set. And all the other flip-flops are cleared. Okay, this is important point which you should have to note it down in case of the ring counter, because at any instant only one flip-flop is set and the remaining all other flip-flops are closed. So for example, if first clock comes, then only one output is there, and accordingly you will have the output, but remaining all outputs are 0. So this is the special case actually. So the frequency is divided by 4, you can say, okay, in context to the applied frequency at the input side. All right. So let me first draw the a block diagram, conceptual block diagram of the ring counter. So to do that, this is the special case actually. We are first time going to construct the counter using the D flip-flop, okay, because all the earlier cases we construct our ring counter using or any counter using T flip-flop, but this time ring counter and Johnson counter we will use the D flip-flop, okay. So this is, let's say in general, this is my D input, and these are the complemented and uncomplemented outputs, and of course one clock input is also there. Okay, so we required 4 such flip-flops, so I am gonna duplicate it like this. Okay, and just because these all register counters are comes under the synchronous design, so we have to provide a common clock to all the flip-flops. So let's say this is the common clock input which we provide to all flip-flops. Okay, so this is the common clock input, and we have set one flip-flop to, and interestingly to set, and in this ring counter we are not going to use these input terminal D. Okay, we are going to set these flip-flops using this preset and clear terminal, which we have discussed yesterday in the lab session. Okay, two additional inputs these flip-flops are having, so we will going to set those flip-flops using those terminals only. But yes, the feedback path is created in this fashion. The output of this flip-flop is set like this.
सर डी फ्लिप फ्लॉप में तो 2 टर्मिनल इनपुट टर्मिनल होते हैं ना, डी फ्लिप फ्लॉप में 2 इनपुट टर्मिनल होता है ना, एक डी एंड डी बार.
D and D bar? No. D flip flop is having only one. D and T flip flops are having only one input terminal. Na bhai?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
धनंजय रिवीजन नहीं हो रहा है, ऐसे कैसे काम चलेगा? So you can see this is the feedback path. Okay, and let me write it this in this way. This is, let's say this is my D3 input. This is Q3, Q3 bar, D2, Q2, Q2 bar, D1, Q1, Q1 bar, D0, Q0, and Q0 bar. Okay, so this is the conceptual block diagram of a ring counter. Okay, this is, you can say, this is the block diagram of ring counter. Okay, this is the block diagram of ring counter. Let's also try to understand this counting phenomena in case of ring counter with the help of this table. So we first write the clock input, then we have to think of the what is the individual output of these flip-flops. Just I told you, you have to input only once using the preset input terminal of the first flip-flop, then it will start generating a shift kind of ones, and that will be only one flip-flop output will be there at any instant of time. Okay, so initially the clock input, then we have, let's say, this output Q3, then Q2, then Q1 and Q0. So for example, in absence of clock, there is no clock. Let me say the no clock with 0. The outputs are, all outputs are 0, 0, 0, 0. We have seen yesterday an experiment. See, yesterday experimental setup, clock is directly connected. You can connect the clock through one switch also. Yes. Hello.
Yes, sir.
Hello.
Yes, sir.
So the experimental files which I have shared with you, in which I am not use one, because once you run the program, then automatically it's a very fast clock is applied to all the flip-flop. But you can use switch at this position. Okay, so you can control the clocks also in that manner. So now, for example, the first clock comes, then of course it will gives the output here, because this will be 1 and the remaining all are 0, 0, 0, 0, 0, 0. And when the second clock comes, the second output become 1 and remaining all become 0, 0, 0. Similarly, when the third clock pulse comes into the picture, your Q1 output is 1 and all other output become 0, 0, 0, like this. And then fourth clock, then this is 1 and all other are 0, 0, 0. Okay. Similarly, if the fifth clock comes into the picture again, then it will again start with 1 like this. This is 1, 1, and remaining all other are 0, 0, 0. And if it is, then again sixth clock comes into the picture, then Q2 is 1, Q2 is 1, and all other outputs of the flip-flops are 0, 0, 0. And for example, if your seventh clock comes, then of course this is 1 and remaining all others are 0, 0, 0, and so on, so forth. Okay, so in this case, actually, your counting phenomena in this, you can say this is once this 1 is going to shift and then it repeat itself. So there is a ring pattern. There is a rotation of this 1 you can observe in this special type of counter. Hence, that's why you can say that these counters are actually count up to only 4 states. So hence we can also say these kind of counter as mod 4 counter. This is very, very important question. Sometimes in your examination, if objective question could be asked like which of the following is mod 4 counter. Okay, and then he can say like BCD counter, ring counter, Johnson counter, and for a few more options will be there. Then of course you have to choose a ring counter as your answer. Okay. And clockwise, if you want to observe this pattern, then of course just we have seen in this case that your clock is divided by 4. So the diagrammatic representation of the clock, individual clock at the outputs, you can observe in this way, like this will be like this. Okay. One, two, three. Okay, so this is, let's say this is the time period t, this is the time period 3t. Okay, and the whole time period from here to here is 40. Okay, 40. So this is your ring counter. Okay, now let's also try to understand in context to the another counter, which is the Johnson counter. Okay.
Sir.
Am I audible?
Yes, sir.
Sir.
Okay, so just wait. Johnson, and again we are going to restrict our discussion with 4-bit only. So let first write the topic name, which is Johnson counter. Johnson counter. And there is a slightly difference between the ring counter and Johnson counter. You will just observe. But before that, let me also tell you that this counter is also known as some very interesting names. Okay, just like this counter is also known as the twisted ring counter. Okay, sometimes again objective question can be framed with this topic. Twisted ring counter. Another name of the Johnson counter is switch tail counter. SWIT, switch tail counter. Another name is walking counter. Walking counter. Another name of the Johnson counter is creeping counter. Creeping counter. These are some synonyms you can say. And one more name, which is a little bit more you can say this is Motrices, MOETRICES counter. Okay, so these all are the name of the Johnson counter. And again, the points which we have written earlier means two important points like these, that in any counter we have these kind of things. So let me copy it and paste it over here. So these statements are also correct in context to Johnson counter, that n-bit counter counts n states, but here the n-bit counter counts 2n states. This is 2n states, and used states are n is equal to 2n, and unused states are 2 raised to the power n minus of 2n. And if the input frequency f is applied, then the output frequency of each flip-flop is f divided by 2. Okay, but yes, of course, in this counter we required some decoding mechanism, because you cannot read the output directly. So what we can say that in this counter, the output need to be decoded. Okay, output need to be decoded. It means you required one additional circuit with the this Johnson counter. And what this decoding circuit is required, let me write again that a total of 2n decoding gate, a total of 2n decoding gates are needed, and these gates are either two input AND gate, or two input NOR gate. Okay, let's try to understand where we actually use and how to construct this decoding network with the Johnson counter. Okay, so but before that, let me first draw the conceptual block diagram of the 4-bit Johnson counter. Okay, 4-bit Johnson counter. So 4-bit Johnson counter, again we require 4 D flip-flops, which we have seen previously, like this. But the only difference between these two counter is the feedback connection. In this Johnson counter, the feedback path is provided from not from the Q0 but from the Q bar. Am I audible?
Yes, sir.
And my board is visual, yeah?
Yes, sir.
Okay. So this is your Johnson counter. Okay. This is your Johnson counter. And now let's try to understand. अच्छा. हाँ ठीक. Let's again try to understand this functionality of this 4-bit Johnson counter with the help of one table. Then let me draw this table with the clock input. This is the clock input. Then we have to focus on what is the individual output of the flip-flop. So I'm going to write this is Q3, Q2, Q1 and Q0. The first case, when the clock is not there, then of course all the outputs are 0, 0, 0. And when the clock comes into the picture, then what happened? The first flip-flop output is 1 and all the remaining outputs are 0, 0, 0. In this case, when the second clock comes into the picture, then 2 flip-flop output are 1 and first clock pulse, then for the second, yes, this is 0, 0. When the third clock comes, then your outputs will become like this, 1, 1, 1, and this is 0. With fourth clock, you will have outputs of the flip-flop like this. Okay, and with fifth clock, you will have outputs like this. First flip-flop output become 0. Then when the sixth clock comes in, then this is like this, and when the 7th clock comes in, then this is 1 and 0 0 0. For the 8th clock all become 0 0 0 0, and when the 9th clock comes in again, then you will have this 1, and this pattern repeat again and again and again. Okay, this is 0 0. You can see an interesting pattern in this Johnson counter, but you can directly not read what happened at the output. Okay, so what to do that? You required one decoding logic. One decoding logic is required to read the output. And how to do that? For example, in the first clock, okay, you have to take the pair. Okay, you have to take the pair of two flip-flop outputs together to make a decoding logic. Okay, and to do that, I am going to take first these two output state, and if you want to write the minterm related to this pair of outputs, so this decoding logic will be called as, this is Q3 and Q2 bar. This is Q3 and Q2 bar. Similarly, you will succeed for the next two pair of the output. Hello, am I audible?
Yes, sir.
Okay, so in that case you have to consider these two pair of output, and you have to write the decoding logic for this. So this decoding logic become Q2 and Q1 bar. Similarly, the next, like this is your Q1 Q0 bar. Okay, then this for this this fourth clock, you have to write the first and the last, so this will be called as Q3 and Q0. This is Q3 and Q0, and then again you will start repeating in this same fashion like this. This is here, this will become your Q3 bar,
Q3 bar, Q2
bar, Q2, then this pair decoding logic will be Q2 bar and Q1. With this, the decoding logic will be क्या होगा?
Q1 bar, Q0.
Q1 bar, Q0, and what about this 8th clock?
Q0 bar. Q3
Yes,
bar,
Q3 bar and Q0 bar. Okay, so this is the decoding logic is required. Okay, so how to implement this decoding logic? Of course, the application point of view, first of all, you have to understand that this specific Johnson counter is actually count up to 4 clocks only. Okay, these are the 4 clocks which it counts.
अगर number of flip flop बढ़ाते हैं तो counting भी तो बढ़ सकती
Yes, but yes, of course, but we are discussing the 4-bit case only, na? So that's why the possible states could be 8 only. Yeah. So that's why one important name of this counter based on the number of counting state, you can say this is called as the mod 8. Okay, mod 8 counter. These are very, very important bullet points, you can say, for your MCQ based questions. Means which of the following is called as the mod 8 counter. Again, he will give you 4 options like BCD, a ring counter, Johnson counter, and some other counter name he can say, and he can ask you that which of the following is mod 8 counter. Okay, So you have to simple mark that Johnson counter is mod 8 counter. Okay. So to implement this decoding logic with this Johnson counter, you required one additional circuit, and that additional circuit is called as in general
हेलो सर
हाँ,
सर ये डिकोडिंग लॉजिक के लिए हम लोग सर ये पेयर क्यों ले रहे थे सर?
पेयर इसलिए ले रहे थे क्योंकि एक सेकंड, फर्स्ट लेट मी ड्रॉ द डिकोडिंग नेटवर्क. Okay, this is decoding network is required, and of course this decoding network का जो input और output है वो connected होगा with Johnson counter. So let me I required more space, so I'll draw it here. Decoding network, and this is my Johnson counter. Let me say this is my 4-bit Johnson counter. Johnson counter, and just we have told you that we cannot read this output in a proper way. So we required this decoding network. So the output of the Johnson counter is connected with this decoding network like this. And of course these outputs are with respect to Q3, Q2, Q1 and Q0, and then you can read any one of the output. Okay, from here you can read any one of the output. Four, 5, 6, 7 and 8. Okay, so any output you can read from any one of the output, any one of the output, which we actually designed using this decoding logic. Okay, and one more thing, that the clock part, if you observe, okay, so just it's a modulo 8 counter, so the clock is means we have told you that if you have provided the clock frequency f, then this will be divide this clock frequency by 2n. We will demonstrate you this entire. I am going to try to demonstrate you the entire functioning of this ring counter and clock counter using your Digitalworks software. But I have one confusion. I never ever tested these counters earlier with this simulator software, but I'll try. But before that, let me draw the clock part of also. So the clock in this case will be look like this, because we are considering 2 outputs at a time. So this will give clock like this. I'm drawing just for the sake of am I audible?
Yes, sir.
Yes, sir.
Yes.
So this is 4t, this is 4t, and total clock duration is 8t. This is 8t, and if we say the clock is divided, f divided by 2n at the output, so if I am assuming f divided by 2n, so this is equal to f divided by 8, because n is equal to 4 we are considering here. Okay, so this is